All right, we are officially at 41 minutes past the hour, so I'll start. Anyone who comes in now can't get mad that I started. Hi, everyone. One more talk to go until the party. I'm delighted that you've chosen to make it this one. Did anyone go to Dylan Beattie's talk yesterday on algorithms? You know when he said, how many of you speak maths? Did anyone put their hands up for that one? A handful. Hopefully, at the end of this talk, you will all speak a little bit more maths, or at least you'll be able to say that you went to a talk where somebody taught you elliptic curves. So I am Eli. I work at a research institute based out of the University of Oxford. But the thing that's interesting about my background for us here today is that I studied maths at university, and they even gave me a degree for it. And what I'd like to do today is talk about some of my favorite maths, which happens to be industry relevant to us because it's what powers the security of our web traffic, among many other things that we take for granted. And it's also an area that is undergoing a bit of change at the moment, which I think is deeply exciting, and I hope that you will think so too after I'm done telling you all about it. The agenda for today is we're going to talk a little briefly about the history of cryptography, and this really is a whistle-stop tour, right? And talk about why we use cryptography and why we need to do asymmetric cryptography. I'm going to talk about RSA, which is one of the first forms of asymmetric encryption and something that you might have studied at maths, as part of a maths degree or as part of a computer science degree. And I'll do a worked example of RSA encryption. I will then talk about elliptic curve cryptography. And this part of the talk is where it starts to get a little bit more vibes-based and a little bit less rigorous. I'm not doing a worked example of, for example, the elliptic curve digital signing algorithm, because I found that it really does put people to sleep. But it is part of the slides at the end, and if you want to see it, I will happily go through it. So I'm going to talk about elliptic curves. There'll be lots of pretty diagrams and things of that nature. Then, talking about quantum computing and Shor's algorithm, which is becoming more and more relevant by the day because we are actually building quantum computers that can do things, which is very exciting, but also scary. After that, we'll wrap up by talking about where we're going next in the world of asymmetric encryption, what it means for you in your day-to-day life, and things that I hope to see as developments in the field in the future. So, a very, very brief history of cryptography. We have been talking to each other for a long time. We have been writing things down for a long time. And a lot of the time, we want to write things down that only certain other people can read. We want to send secret messages to each other. And one very rudimentary way to do that is once you have an alphabet, you can do things like substitution ciphers. So this is, NDC is great, my secret message that obviously I want to impart only to all of you and not anyone outside this room so that nobody else comes to this conference and we get to keep, this is exclusive club for us. And what I've done here to encrypt this is I've taken each letter of the alphabet and I've shifted it along by 6 characters, right? So an A becomes a G and so on and so forth, right? We can think of the letters here as numbers. They have a numeric value that corresponds to their position in the Latin alphabet, and we're simply applying an operation to each of those numbers. And in this case, it's a flat +6 to all of them. This is called a Caesar cipher, and it was at one point military-grade encryption because Roman military used it. That's where it gets its name. But it's very easy to break with things like letter frequency analysis. Like when we write natural language English, we know certain things about the pattern in which letters appear, their frequency, their relationship to each other, and we can use that to break this kind of encryption. So this is very weak. But another thing we can do is we can say, okay, this is the worked example of the next iteration of this, which is my message, NDC is great, and its numeric representation. And instead of adding just 6 to every number that represents a letter, I'm going to take a second phrase, my key, my private key phrase, and this has a numeric representation as well. And it looks like that. And I'm going to add, pairwise, each letter to its corresponding letter of the private key, and I get out some numbers. We take the modulus of 26, because there's only 26 characters that we care about for the purposes of this message, and that becomes a message at the end. And in order to decrypt this message, you would need to know the private key that was used to encrypt it, right? This is unbreakable mathematically, pretty much. This is the computation that you would need in order to break this. Simply, you just have to know the private key. And that's fantastic, right? Except that if you want to use this method of encrypting messages, you first need to have a shared private key that only you and your person that you're talking to knows. How do you get to that situation? That's a chicken and egg problem, right? So symmetric cryptography requires both parties to already be in possession of some kind of shared secret. And if you have a private key that's long enough, if it's as long as the actual message you're trying to encrypt, it's unbreakable. Any shorter and it becomes a little bit weaker. But with a long enough shared message, a shared private key, you can do symmetric encryption, and this is very secure, very cheap to do computationally. But it's very difficult to get to that stage. And what this talk is about is how we get there. Asymmetric cryptography is essentially an implementation detail, right? It relies on mathematical properties, mathematical problems that are very difficult to solve. So when you're trying to break asymmetric cryptography, what you're trying to do is solve math problems that we know to be like computationally difficult to solve. And where this is used today is basically in order to get to a point where we have a large enough shared secret that we can use it for symmetric encryption. And so if you go and look up how the TLS handshake works, Scott Helm has an excellent talk about this, and there's loads of great resources. You can see that asymmetric cryptography is used for that initial setting up of a shared secret, and then the bulk of traffic is actually done with symmetric encryption because it's cheap and very strong. So asymmetric cryptography allows us to use symmetric cryptography. That's mostly what it's used for. And the first example of this that we really have that's sort of famous is the RSA encryption system, crypto system. And this relies on some maths, that is group theory. So RSA, it was first published officially by three mathematicians called Rivest, Shamir, and Adelman, hence RSA. And they officially published it in 1977, which is actually much longer ago than I think it is, nearly 50 years, my goodness. It was also independently discovered by a guy called Clifford Cox at GCHQ in the UK in 1973. And the folks at GCHQ said, well, that's cool, I guess, that you've found this sort of weird maths thing, but I'm sure it has no practical application, so let's just put it in a box and lock it away in the vaults. And then 4 years later, people came up with it publicly. Hello, Randall.
So if they'd gone the normal way and put their names in alphabetical order...
Yes, they didn't. Yes, it would be. Do you want me to say that out loud for the YouTube video? Randall points out that if these three mathematicians had put their names in alphabetical order, it would be the R's algorithm or crypto system, and also independently discovered by somebody called Cox, so the R's Cox crypto system. Thank you for that, Randall. We're doing a talk about cryptography together in Copenhagen, by the way, if anyone's going to that, so more... And this crypto system, the hard maths problem that powers it is the fact that if you have a very, very big number with very, very few prime factors, it's really hard to find those prime factors. But if you have big prime numbers, it's cheap to multiply them. So it's a sort of one-way operation. And I will now go through a worked example of this in practice. So we're going to take our really, really big prime numbers, 17 and 19, because we can actually kind of fit those in our head, and they multiply to make 323. And we're going to call that number n. In order to do encryption with RSA, we need to know some numbers that relate to these numbers on the screen. First one we need to do is we need to find something called lambda n, which is also called the Carmichael totient. And this is a number that you can compute from n, 323, if you know its prime factorization. You can compute this easily. And the property of this number is that for any number, 1, 2, 3, 4, 5, up to 323, if you raise that number, let's say 5, to the power of this special number Carmichael totient, and then you take the modulus of 323, you will always get a remainder of 1. And this might sound really, really hard to find, but if we know the prime factorization of n, we can actually find it quite cheaply with this formula. You take the lowest common multiple of the Carmichael totient of the two factors, and the Carmichael totient of a prime number is simply that number minus 1. So for 17, it's 16. For 19, it's 18. So for 323, we get the Carmichael totient is 144, because that is the lowest common multiple of 16 and 18. And what this means is that for any number, we can raise it to the power of 144, and the number will always have a remainder of 1 when you divide it by 323. So we have this special number, and this is secret because it relies on knowing the prime factors. So only we know this, because our private key sort of depends on knowing the prime factors. The next thing we need to do is we need to choose some number that doesn't share any factors with n. So we can't use 17 and we can't use 19. And it makes it easy to use a relatively small number. We don't want it to be too small, but relatively small. And for this example, I will choose 5. And the next thing we need to do is we need to use these things to compute our private key. The private key is a number d that multiplies with e to make something that is one more than a multiple of 144. Lots of modulus arithmetic in that, and we'll come back to that later. In our example, we can use 29 because 5 times 29 is 145, which is one more than 144. And to find this number d, we needed to know the prime factors of 323, because we needed those to know that 144 was our Carmichael quotient, and we needed that in order to get the 145 that these things multiply to. So this number d is secret, and we don't share it with anyone. Now, these things make up some of these things make up the public key. What we share with people when we want them to be able to send us secret messages is our big number n, 323, and our little number e, 5. And our private key is d, 29. So let's say that somebody wants to send us a message, and they want to send us the message NDC, which is 14, 4, and 3. For the purposes of this kind of encryption, all messages are essentially numbers in one representation or other. They might be using binary, they might be using base 16, whatever. 14, 4, and 3. Somebody wants to send us these numbers without anyone else knowing that they have sent us these numbers. The way that they do that is they raise each of these numbers to the power of 5, which is why it's nice that e is kind of a small number, because that makes this computation cheap. And then what they do is they take the modulus of 323. And something you might notice is that because 5 was a little bit small, 3 to the 5 is not actually bigger than 323, so that last step of taking the modulus, 323, does nothing to 243, right? And that's not good. That's why you don't want e to be too small. So they send us these three numbers, 29, 55, 243. So now we're on the other side of the equation. We're back to being the person who has received this message. Somebody's wanted to send us something, and they've sent us these numbers. How do we get back to the original thing that they wanted to send us? Well, what we do is it's very similar to the step that they took to send us their encrypted message. We raise each of these numbers to the power of 29. And this I did, and then we take the modulus of 323 again. This I did not do by hand. I did plug it into Wolfram Alpha. 243 to the 29th power is a really big number. Don't do this at home. But I promise you that it comes out to be 14, 4, and 3, and I will explain why. Here's how this works. When you raise a number to a power, and then you raise it to another power, you can multiply those two powers together, right? So 3 to the 5 to the 29, you can multiply that 5 and 29 together. It's the same as 3 to the 145. And we know that 3 to the 145 is 3 mod 323, because that's what 145 is. It's 3 to the 144 is 1, and then you multiply it by 3 again, and you get back 3, right? Have I lost anyone here? Cool. That's why this works, right? This special mathematical property of the Carmichael quotient that was secretly, we could derive it because of our secret knowledge of the prime factorization of 323. So yeah, that's why it works. You're raising something to the power of 145, which is 1 times the number, it's that what you get out is the number that you started with. But while the number is sort of in transit, only partially raised to the power of 145, nobody can do the second step, because to know what the second step is, you would have to know the prime factorization of 323. And this breaks if somebody else knows the prime factorization, because then they're able to derive your special Carmichael quotient and find a number that works to decrypt the message. So, limitations and considerations. This is, it requires large prime numbers. These can be expensive to find, they can be expensive to verify. It's not quite as bad. So news that happened recently, I think last year, or maybe it was earlier this year, they found a new biggest Mersenne prime number. That it's not quite as expensive to find numbers that you use for RSA. You can use much smaller numbers, but it's still computationally expensive, and you still want to keep those numbers secret. If everybody knows, like, every list of every big prime, they could just kind of sort through them and see if any of them work to break your crypto system. If E is small enough, our number that was 5 in that worked example, you can be in a situation where you raise something to the power, you take the modulus of your big number n, and it does nothing. That was 243 in our example. And if I'm watching the traffic and I see that somebody sent the number 243 and the power that they raised it to was 5, I can just take that route, and I know that 243 is a 5th power. I can just take the route, and I go, well, the last number there must have been a 3, right? So you want your E to be big enough to kind of prevent that happening frequently, but not so big that it becomes very computationally expensive for people to encrypt and send you messages. And the last thing is, because of some of the mathematical properties of this that I would love to go into if I had like 3 hours, you can be vulnerable to a kind of attacks where if you have a suspicion that some part of the encrypted message, you can use that knowledge to try and gain information about the rest of the message. For example, if somebody suspected that somebody wanted to send me NDC, they could encrypt that message themselves and see if it matches what I had been sent. And that's the sort of degenerate case where they guess at the whole message, but guessing at only part of the message can still give you information if you're an attacker, an eavesdropper. Padding in this case is a way to get around this. It's a way to sort of obfuscate against that kind of attack. And a fun little sort of historical tidbit is an example of padding from before asymmetric encryption. I think this must have been a message that was encrypted symmetrically somehow, because this is from 1944, October the 25th. This is a message that was sent to Admiral Bull Halsey, and this is the plain text. And you can see in pink we've got padding, and then in blue we've got these delimiters that denote where the message actually begins and ends. And what happened here is that Admiral Bull Halsey, whoever decrypted the message, managed to miss the last delimiter and included the world wonders as part of the message that was transmitted to him. And so this message is saying, like, where is RPT? Where is Task Force 34? The world wonders. And he interpreted this as a kind of passive-aggressive, like, where are all your guys? Everyone's wondering where your guys are. And he went and he had a little tantrum in his tent, apparently. But this is what padding is, and it's a very common technique in cryptography to just sort of obfuscate against certain kinds of attacks. So in that example, we used a lot of modular arithmetic. And this is because of group theory, which is my favorite kind of maths. Has anyone studied group theory in school, university? Like a couple of hands? So I am going to teach you what a group is, and then we're going to explain why, I'm going to teach you what a group is, and then we're going to see how elliptic curves relate to this. So here are all of the numbers mod 11. It's like a clock. We're all familiar with modular arithmetic, whether or not we know it, because that's how clocks work. And instead of having 12, we've got 11. And the way that this number system works is that anytime you work like normal arithmetic, you can add things, you can multiply things. Although for this case, we're just going to consider addition. And every time you get to a number bigger than 11, you take the modulus. And then you're back within the ring. You're back at one of these blobs, right? So what happens when we want to define a group is we need 4 things that exist within. A group is a set of objects and a way that you can combine 2 objects to get a third object. So in our case, we're going to say that our objects are these numbers, and the way we combine them is adding them to each other. And you need 4 things in order for that, the set of things and the operation to constitute a group. The first thing you need is an identity element that is a non-op when you combine it with other things. And for us, that's 0. You add something to 0, doesn't change the thing. You add 0 to something, you still get the same thing out. And that's why 0 is in blue. It's our little identity element is what it's called. The next thing you need is that every number needs to have some number in the group. Each one of these pink blobs needs a pink blob that when you combine it using our addition operation, you get back to the identity element. And in our case, this will be, each element is opposite its inverse, like by sort of symmetry, vertical symmetry, because you add 10 to 1 and you get 11, which is 0 mod 11, right? And you add 6 to 5 and you get 11, which is 0 mod 11. So in our case, the inverses are opposite each other. And things can be their own inverse. 0 is its own inverse, always in every group. And you need they all need to have an inverse in order for this to be a group. This means you can always get back to the identity element. The next thing you need is something that's called associativity, which is what you get. What that means is that if I want to combine 3 things, it doesn't matter which of those addition operations I do first. These two, 1 plus 4 plus 2 is the same as, well, 1 plus 6 is the same as 5 plus 2, right? It doesn't matter which order you do the combinations in. This should all be sort of familiar to us because this is how everyday maths works, and the set of all numbers is in fact a group, right? And the last thing we need is something called closure, which means that when I combine any 2 numbers, I get something that is still in my set of objects. And this is true in this case because we always take the modulo of 11 and we get back to something that's one of these blobs. So with all these 4 concerns, with all of these 4 conditions satisfied, we can say this is a group. And the reason this is cool is because it allows us to apply lots of cool theories and sort of do lots of interesting mathematical things with it, including asymmetric encryption. And the other thing about groups, well, so we've used a fairly concrete example here that is fairly familiar to people of the numbers, like numbers that we're familiar with. However, it is also, it gets a bit more abstract than that because we also have multiplication with regular numbers that we're familiar with. And this does work in this group, but I want to make it clear that it acts a little bit differently when you're talking about groups in the general case than it does with this specific example. So here, let's say I have the number 4. I have my blob 4 specifically, which is also the same thing as 15 and 26, right? If I want to add it to itself 13 times, I can do that. I can sort of bounce around the number ring and add it. But that's really tedious to write out. And we actually have a shorthand for adding something to itself lots of times. It's called multiplication. And we can do this in here. We can say, okay, 4 times 13. In our regular maths, that's 52. We take the modulus of 11 and we get 8. And now we're back inside our circle, right? So we've done multiplication to one of our blobs and got another blob. But the 13 that I've used here it isn't the same as something that's in the group. It's shorthand for we combined this thing with itself 13 times. And that distinction doesn't mean much when we're talking about these kind of numbers because that's also how regular maths works. But let's say we also have, let's say that instead of these numbers, we just had a set of arbitrary objects that had the same relationships to each other. When I combine the sun and the circle with the cross through it, I get back to the smiley face, and the smiley face is the identity. And suddenly now, it doesn't make as much intuitive sense to say, well, if I times the star by 13, I get back to the club symbol. But the relationships all hold true. And so what that shorthand is saying is that if I combine the star with itself 13 times, I get back to the club. How have I lost anyone here? I have lost Rendell. We're essentially saying, okay, here, this is an example of something that's called group isomorphism, which does not help your confusion. But what it means is that these 2 things are the same under the hood, right? This is a cyclic group. I'm trying to do the pointer, but it's really not. This is a cyclic group, and all cyclic groups with 11 elements in them are really the same thing, and you can think about them as the number wheel. But we're about to look at a group that is not immediately apparent that you can think about it this way. So I'm trying to introduce that abstraction now before we look at an elliptic curve that is this. Spoiler alert, it's the same as this group. Right, so this is group theory. You have a set of stuff, and you have ways that you can shove them together and get something else that's also in that set of objects out. And if you have those 4 conditions, you can say really interesting things about the way that they behave. Right. Oh my goodness. So another thing that is a group is the set of all of the rotations of a cube. If you turn it one way and then turn it another way, you get to another rotation. And you can combine them and reverse them, and you get back to the original orientation that you had. And that's another, it's much more abstract than numbers, but it's still something you can sort of think about in 3D. So here is the sort of formal definition. You've got a set of stuff plus some operation. And in our case, we used like the plus symbol to indicate this. And the 4 conditions that you need to satisfy in order for it to be a group. Right. Elliptic curves. How are we doing on time? 25 minutes. That's not bad. Has anyone studied elliptic curves as a mathematical sort of thing before? All right. Well, I'm honored to be the ones to introduce you to it. And this is much more of a sort of vibes-based thing. There is not, I'm not doing the worked example because it really is like quite dense. So what is an elliptic curve? Well, it's an equation, basically. And it's an equation that looks like this. You've got y squared is x cubed plus ax plus b for some numbers a and b. And when you graph it, it looks something like this. There's lots of different ways it can look, but this is the nice one. There are lots of different cases that don't work well for encryption, for example. And it's a curve. It looks like this. And what we care about is we only care about the solutions to this equation where x and y are whole numbers on some number ring. And in the number ring we just looked at, that number was 11. And what we call that in general is z, which is the natural numbers, which is the integers. And then we put a little subscript there to say we're taking the modulus. So zp means all of the numbers mod p, like for some prime number. And we only care about, for our purposes, the solutions to this equation where both numbers live in that number ring, right? So we're not thinking about like the whole graph, we're thinking about like a little subset. Well, we're thinking about a space that's only like, for our purposes, 11 by 11 blobs wide. And what we have is we have a way of combining our points together. So what we do is we say, okay, we're gonna say that there's some identity element, and we're gonna call it the point at infinity, because infinity squared is the same thing as infinity cubed plus some number times infinity times plus some number. Like infinity satisfies this equation. And this is kind of a fudge, but it's a thing we do in math sometimes because it makes things work nicely. And we call that's our 0, right? And the way that we add points together is if you draw a straight line through your curve, it'll touch some number of points. And we say that if it touches 3 points, those 3 points sum to the identity. So for a particular example of this, let's say we've got 2 points, 2 blobs on our curve, A and B. And I want to add these together because I can do that. I want to prove that this is a group. So what I do in order to add them is I draw a line through them and it hits another point on the curve, C. And you can prove that this is always true. You can prove that there is a blob that satisfies this. So what does it mean? How can I know what C is? And how can I know what A plus B is? Well, we know that A plus B plus C sums to 0, right? That's the law that we have defined, which means that C is the identity minus A and B, because we have inverses. So we have plus, we also have minus. So we can say C is the same as minus A plus B. So we have a way of neatly getting from A plus B is minus C. Well, what is minus C in this world? So when you draw a line through a curve like this, a lot of the time, it'll hit 3 points. But there's a case where it doesn't. For example, if the 2 points are like this, one directly above the other, when you draw a line through that, it doesn't intersect the curve again. But we do say that it intersects the point at infinity. So we say that, okay, A plus B is equal to the big blue 0, right? Or so we say that it's intersecting the point at infinity, and therefore those 3 points sum to 0. So A is the same thing as minus B. So when you have a point on the curve, its reflection below the x-axis is its inverse. So if we come back to our nice line that did intersect 3 times, and we say, okay, A plus B is minus C. What's minus C? Well, it's that point there. This is how we add points together. And you can prove that this satisfies the group law. So we have a bunch of points that we can start saying nice group theory things about. And that's what an elliptic curve is, basically. It's this mathematical equation that you can solve within the modulus of some big prime number, usually a big prime number. And the points that you get as solutions to that equation, you can combine them in interesting ways and use group theory about the ways that that works. Here is an actual elliptic curve that I worked out by hand. It took me probably about 2 hours and a lot of pen and paper. I chose this equation, y squared is x plus 5, and the solutions to that in mod 11 are these coordinate points. And you can kind of see that it looks like that curve, right? Like a little bit. Right. And I'm going to show you how this is actually the same thing as the number wheel that we looked at earlier. When you do elliptic curve cryptography, you need to publish a set of parameters about the curve that you're using. And one of the things you need to do, so the curve that you're using is kind of analogous to your big number 323. And then you also need to do something. Do you remember we picked that number E5 as part of our public key? We do a similar thing. So we have to pick a point on this graph. And the parameters that we use when we publish our public key about our curve, they look like this. And this is just basically straight from Wikipedia. What we need to let people know if they want to send us a message is P, which in our case is the 11, because it's the integer that we're doing modulus with. We need to give A and B, which are the things that define our curve. In my specific example, it was 1 and 5. We need to say our special point. We pick a special point on the curve, and we say this is our special point that we're going to publish. It's sort of equivalent to E being 5 in our RSA example. A number N, which is a group theory thing that I don't really have time to go into, but in our case, it's pretty much always going to be 11. And H, which is 1, which is generally your P divided by your N, pretty much. I'm hand waving here, that what I'm saying is not entirely rigorous, but we'll go through and look at how we get each of those out of our curve. So what we have here is we're going to pick like a special point on our curve. We're going to start filling out our curve parameters. So P is 11, as I said. A and B are 1 and 5, and we get those from our equation. We pick a special point that's our favoriteest point in the world, and we publish that, and we tell people, here is a solution to this equation. And we say 11 and 1 are the last two things. And that's just, those are some mathematical properties that you would need to know in order to do like the computations, not that relevant for the kind of hand waving that I'm doing right now. For those of you who came to Dylan's talk yesterday and he said, you know, Wikipedia maths pages, who are they written for? What's the audience? Is it people trying to do implementing algorithms? Is it people trying to like do research? What is it? It's me. They were written for me. I love this stuff. And the interesting thing about this is the Wikipedia page for combining points on an elliptic curve, which formed a large part of my browsing history during the writing of this talk. The interesting thing about this is that it gives you some equations. If you've got those 2 points and you know their coordinates, you can do this to get the point that they sum to rather than having to like draw a line and kind of eyeball things. So using these equations, we can do point multiplication and point addition of our blobs. And what we find out is we take our special point and we add it to itself a bunch of times. And I did all of these calculations by hand, and I scrapped at least a couple of curves because they didn't work the way that makes them nice for this example. But what we find is that if you add 0.4, that's 0.4 to itself, one time, you get another point in the curve. And if you add it another time, you get a third point in the curve, and so on and so forth. And what you end up with is this. You end up with 1g is this point in the curve, 2g is another point in the curve, 3 is another. And something I'd like you to notice, we remember that the inverses of points in the curve were their reflection in the x-axis. For example, 4 lots of g is the inverse of 7 lots of g because they're the same, but they differ in their y coordinate. It's opposite. This is the same structure as the number wheel, right? If you added 4 and 7 to each other, they're inverses, so you'd get back to the point at infinity, which is 11, 0, which is the same thing as 0, because we're working in mod 11. Have I lost anyone on the hand-wavy vibe front? This is not as rigorous as I'd like it to be, but does this make sense as a way that this elliptic curve, this set of blobs, is actually under the hood the same thing as that number wheel, right? And that's why elliptic curves work for cryptography. And I will happily go into lots more detail about this for anyone who's interested, but it tends to put people to sleep if I actually do it as part of the talk. And this is why elliptic curves work for the same kind of cryptography as RSA. You can do a very sort of similar, analogous way of sort of combining things and decrypting things. And it's not exactly the same. The main thing we use elliptic curves for is actually digital signing rather than encrypting things. But one of the things that this gives us is an advantage over RSA, and elliptic curve cryptography has superseded RSA in a lot of cases, is that it's actually a lot faster to do. It's computationally efficient. You get a smaller key size per security, which means that essentially, yeah, you have to use fewer computational resources in order to send a message that is as difficult to attack. Smaller payload size, again, it's all about sort of the efficiency. You can be very, very quick with these kind of calculations. Yeah, and this is why elliptic curve cryptography has superseded RSA. It's a sort of, condensed version, almost. And it's powered by a very similar math problem, and we'll go into that later. And this is fantastic, right? This is the modern world. We've got encryption. It's very, very fast to do. We've got the TLS handshake. It works great. People can't read our web traffic. We have things like internet banking, and we can sign our Git commits. And we have YubiKeys that will allow us to log into, web apps without being traced. Things like this. Fabulous, right? End of the talk. 36 minutes. Great. Wrap up. It's not that easy because we, among many other things that humans have done recently that cause us lots and lots of problems, we developed quantum computers. So in 1994, Shor published a set of algorithms, a mathematician called Shor. He published a set of algorithms, and quantum computers didn't exist at this point, but people theorized they might, and they were able to talk about how they would work. Because we had, the quantum theory to do it, we just didn't have the engineering to physically build such things. And Shor published a series of algorithms, and these algorithms solve the hard math problems that power this kind of encryption. So the kind of the hard math problems that we have based things on so far in this talk is the integer factorization problem. You've got a big number, it's hard to find its factors. There are two other problems that go into making elliptic curve cryptography work, and they're kind of the same thing. It's easy to do a computation one way and hard to reverse it. The discrete logarithm problem, which is a group theory. If you have a blob and you add it to itself a lot of times, sometimes you get the whole number circle, sometimes you'll only get half the number circle, sometimes you get like a subset of it, and that's called a subgroup. And it's really, really hard to find if you've got one blob and another blob that you can get by adding it to itself a lot of times. It's really hard to find how many times you had to add it to itself. Again, hand wavy, but it's an operation that's cheap to do and hard to undo. And similarly, the elliptic curve discrete logarithm problem, which is basically the same thing but specialized into the language of elliptic curves. And Shor's algorithms, Shor has an order-finding algorithm, and I'm going to show you a worked example of this breaking integer factorization, this problem that is proven to be hard to solve with classical computers, but Shor's algorithm breaks it. And this is the one I think which people typically call Shor's algorithm. He wrote more than one, but this is the really famous one. What this does is it tells us that if you have a quantum computer big enough, it is easy to take some number n, let's say 323, and you pick a number a somewhere between 1 and n, and in the worked example, I'm going to use 11. What we can do is we can take those inputs, and in polynomial time, we can find the number that is the smallest number, such that when we raise 11 to that power, we get something that's 1 mod 323. And this might not sound that difficult. It might not sound that powerful, rather, but this is hard to do. This is impossible with classical computing. But in polynomial time with a quantum computer, we can get this, right? So with that superpower in the back pocket, let's see if we can factorize 323. So n is 323. We happen to know that it's 17 times 19, but for the purposes of this, let's pretend we don't. I've chosen a is equal to 11, and Shor's algorithm tells us, within polynomial time, that if you raise 11 to the power of 48, that's a number that has a remainder of 1 mod 323. Used Wolfram Alpha for this. Don't do that at home. Took me a long time. I was really glad I didn't have to go back and do it a second time, because that can happen when you're trying to do this computation, which I'll get into. If you don't get an even number here, if it had been 11 to the 47, we'd have to start again and pick a different number, not 11. We'd have to pick any other number. But because it's an even number, we can do some interesting stuff. So 11 to the 48 is the equivalent to 1 mod 323. which means that 11 to the 48 minus 1 divides by 323. And that's the difference of two squares. So we can factorize that. And we know that 11 to the 24 minus 1 times 11 to the 24 plus 1 is a number that divides by 323. So either the factors of 323 all go into one of those two things, or they're split between those two factors, right? Either both 17 and 19 divide one of those bracketed expressions, or it's 1 and 1, right? Now, we know that that can't be true for the one that's 11 to the 24 minus 1. We know that they both can't go into that, because 24 is smaller than 48, and Shor's algorithm told us that 48 was the smallest number for which that was true. So at least one of the factors of 323 has to divide 11 to the 24 plus 1. And now that we know this, we can do some very cheap classical computation. We can do the greatest common divisor of these two numbers. This is cheap to do on classical computers. And when you do it, you're finding the biggest number that divides both of those numbers. And sometimes that will be 323. Both the factors went into these two things and you haven't learned anything. But about half the time, it won't be true, and you'll find a factor of 323 that's less than 323 that divides both of them in a way that is cheap to do on classical computers. And then you found a factor of 323, and you've broken RSA, because now I can do things like find your private key and decrypt messages that people have sent to you, because I can calculate the Carmichael quotient that was 144 and find that D, your private key, was 29. Does that make sense? This is probably the densest bit of the whole talk. Good? Looking a bit shell-shocked. So that is Shor's algorithm breaking the integer factorization problem, which means it breaks RSA. And that's pretty bad, right? We've solved one of the problems that powers our encryption. But it's fine, right? Because we have elliptic curve cryptography and it's powered by these problems. Yeah, bad luck. Shor breaks those two, unfortunately. So RSA and elliptic curve cryptography are both vulnerable to Shor's algorithms for quantum computers. And this is really, really bad because that's how we encrypt our traffic. And just because we don't have quantum computers today that can do that, I think the most recent development was they managed to build a quantum computer that did use that Shor's order-finding algorithm to factorize to factorize a number that was the product of two primes. It did something groundbreaking. It proved that 15 is 3 times 5. But we'll get there, right? And the worst thing about it is that it's very cheap to store data. And so there's a thing called the harvest now, decrypt later paradigm threat. You know, that's the phrase, like a harvest now, decrypt later, where people can just store all the traffic that they're looking at. It doesn't matter if they can't read it now, because in 25 years they might be able to. And you know, if your data is still relevant in that time, let's say you're a nation state actor, that's really, really bad. Like this is like these encryption algorithms, these crypto systems are compromised. And we know that they're going to be compromised in the somewhat near future. So what do we do next? Well, the answer is that these aren't the only 3 hard maths problems in the world, thankfully. Otherwise, lots of mathematicians will be out of a job. And this is where we get post-quantum cryptography. We need to find some other hard math problems that we can use to develop crypto systems. And these hard math problems need to be not vulnerable to any known quantum computing attacks. And so this is what mathematicians have been working on, cryptographers have been working on for, well, basically since 1994, I think. They've been looking at other things that we know to be very hard problems to solve and seeing if we can use those to develop a way of sending encrypted traffic. One such example of a hard math problem is the isogeny finding problem. Given two elliptic curves, we know what those are. We know that there exists an isogeny between them, and we need to find the mapping that describes it. I could probably understand what this means with, like, you know, a few days of reading Wikipedia, of reading maths papers. You don't need to know what it means, but it's a hard maths problem, and it's based on some of the same maths that we've just talked about, but we theorize that it's not vulnerable to quantum computing. Unfortunately, the algorithms that, the crypto systems that people developed based on these were actually considered insecure. Psych and Seed, yeah, there was something that was called Seaside. It was what is it, what is it, have I got the thing here? I forgot what the C stands for, but it stands for the super singular isogeny Diffie-Hellman process. It was called Seaside because the people who were working on it worked on it in like a house by the seaside, and so they called it Seaside. But unfortunately, it's only around half as secure as you would expect it to be for the amount of computation that you have to do, which is a shame. But as a proof of concept, we've seen that we can use other hard math problems to develop crypto systems. They aren't secure classically, but it's not because the quantum computing is the threat. So that particular math problem didn't shake out. We tried some other ones. The learning with errors problem, and this is witchcraft to me. Like, I have a maths degree. They let me out with the magic piece of paper, but this is beyond, this is really like insane stuff. This basically, as best I can understand it, involves kind of adding probabilistic noise to the way that you encode things and then using some kind of magic to remove that noise at the other end. And this, turns out, we did get some good crypto systems out of it. Crystal's Kyber, which is for key encapsulation, which is remember back at the beginning I said that all of this is kind of an implementation detail allowing us to do symmetric cryptography. That's key encapsulation. You encapsulate a key, and then that key is what you use to do symmetric cryptography. So Crystal's Kyber does that for us. And there's also Crystal's dilithium, which is used to generate signatures. That's what like your YubiKey is doing, for example. And these are in use today now. This is from Google, and this is an example of what they are saying you should do. They're recommending that you do in order to use dilithium, this key encapsulation, this signature, alongside current elliptic curve cryptography. They're saying you should sort of nest them. And that way, even if somebody does manage, even let's say that tomorrow somebody finds a weakness in dilithium and it's broken and we have to start over again, you're still somewhat protected by your elliptic curve cryptography. Similarly, you can also do this. This is what Chrome does when you enable post-quantum cryptography in it, which I think might be hidden behind a feature flag. They might have actually made that, that might be in general release now. I should have checked. But what it is that you have, when you do a key exchange for TLS, it will generate half of the bytes using one crypto system and half using the other, hedging your bets a little bit. And this is in production. This has been in production for a while, or this has been in the feature flag version of Chrome for a while. So this is stuff that you can use today. So post-quantum cryptography is addressing a need that we don't technically have right now, but we know we have it for the future. And if you are somebody who thinks that you might want to protect yourself against the harvest now, decrypt later threat, you should enable this. It's good practice to do it anyway. Cloudflare has also enabled these kind of things on all of their sort of all of their infrastructure. So it's becoming easier and easier to do this kind of thing. There's a really interesting project called Open Quantum Safe, which is developing some of the libraries that are being used, so a lot of C libraries, in order to actually implement these algorithms. And so there's actually an article that I got sent yesterday, courtesy of Rendell, about Microsoft enabling a lot of this stuff more widely. So both on Windows and Linux, they're just sort of rolling these things out in various bits of software that they control. So yay, Microsoft, I guess, for that. More security. This is an article from yesterday, and it's essentially talking about the productionization of a lot of these algorithms. So there's, alongside the Crystals algorithms, there's also something called, what's it called? It's a stateless hash-based digital signing algorithm, which is using a different kind of maths that I also don't understand, but it's very cool, and we can be relatively sure that it's not vulnerable to quantum. And when I say relatively, I mean people have been trying. This is the sort of hot area of cryptography right now. So this is stuff that we can do today, and I highly encourage you to do it. Just because Shor's algorithm breaks all of the sort of encryption programs that we have had developed up until these new ones, doesn't mean that your traffic is insecure, but it does mean you should probably start enabling these kind of post-quantum algorithms in any infrastructure that you have control over. So, where next? Things that I hope to see. So, one risk that I see, and again, I'm not like a career cryptographer, but I feel a little bit anxious that these hard maths problems on which we are basing our new crypto systems might also get broken by as yet unwritten quantum algorithms, right? So if we have more math problems and more crypto systems to choose from, we hedge our bets against those. We protect ourselves against the one thing on which we rely getting broken. So we could do the learning with errors as that's one, the hard math problem that gives rise to the crystals algorithms, but there are other candidates too that are being worked on. So I'd like to see a whole ecosystem of these kind of things so that it becomes less and less likely that all of them become vulnerable to some kind of attack that we discover in the future. I would also like to see quantum resilient hardware tokens, because I think hardware tokens are just the coolest thing ever. Please come talk to me about them. It's really, really cool. And I'd love to have an object that I'm like, this is my quantum resilient hardware token. Like, that's living in the future. That's really cool. And I would like to see these things become more and more productionized, more and more accessible to people. I'd like to see better sort of understanding among developers that of this field and what it means for us, and keeping our customers safe, keeping ourselves safe. And this is me doing my bit to try and be the change I want to see here. I would love to see this become more of a talking point, and for us to be less intimidated by it, because I think that is a thing among developers as you go, oh, the quantum cryptography, or it's scary, or whatever. It's not. It's a toggle you can switch in Chrome, and it's a setting you can set in Cloudflare. But understanding why it matters helps you make more informed decisions about where you use it. So, wrapping up, we have had 51 minutes of maths. We have had how we got here, all the way from Caesar ciphers through to post-quantum encryption. We've talked about RSA, ECDSA. I have given you a fairly rigorous treatment of RSA and a very hand-wavy one of elliptic curves. We've talked about quantum computers and why Shor's algorithm, how it works, how it can actually break the encryption that we use today, and the fact that actually the encryption we use today is lots of new and shiny stuff that is available for you right here, right now. That wraps me up. Here's a QR code that can take you to a little form, just a free text field to give me any feedback that you have. I really appreciate it. It helps me make the talk more useful for other people in the future. And we have time for questions, or you can go and get a head start on the party. Thank you so much for your time and attention.